welcome to CPE 329, Programmable Logic and Microprocessor-Based System Design. This lecture is going to be a microcontroller survey. So in this class we've used the ATmega 328P. And many of the things that you've learned in 329 will apply to any other microcontroller. The biggest difference really is the naming of the registers. So first, what is a microcontroller versus a microprocessor? A microcontroller usually has a CPU, memory, and other peripherals all on the chip, whereas a microprocessor may not necessarily have all of these things, or may just have rudimentary I/O ability. So, for instance, your like Pentium class or desktop class processors, they have other I/O chips that allow it to have high-speed I/O to, let's say, memory. So microcontrollers were really thought as single-chip computers and appeared around the mid-70s. And many microcontrollers have evolved into microprocessors like the x86 or the 68000 or IBM PowerPC. Most of these aren't around anymore. So microcontrollers, they typically come in a large family, so we've seen this in actually in the ATmega sense. When you built the project, there's a load of different microcontrollers out there. A lot of them are just simple memory variants or I/O variants, like it may have more timers and more PWM, more memory, things like that. They can build up a family of microcontrollers pretty quickly. There used to be 4-bit microcontrollers used to be pretty prevalent, but they're pretty much all but gone because it actually costs quite a bit to make the package for some of these small microcontrollers and test them. And silicon costs have gone way down because we can shrink down our transistors into such small sizes. So most microcontrollers now start in the 8-bit side. There are 16 and 32-bit microcontrollers, and we can see that even the 8-bit microcontroller market share here has been falling, where these other slices have been growing. And then there's also another class of microcontroller I'll talk about, which is called digital signal processors. So are there more microcontrollers in the world than microprocessors? The answer is yes. And I guess this is a market study here. It's about 14-to-1 microcontrollers to microprocessors. But actually, which one generates more revenue? Microprocessors do. They can charge a lot more, a few $100 for a microprocessor. Some microcontrollers are under $1 nowadays. And I think that the line between microcontroller and microprocessor is actually being blurred as well, because you have these like smartphones and things like that, and they're actually pretty high performance microprocessors with microcontroller features. So we'll talk about some old stuff. The HC12, Motorola, and the 68000 for Motorola. They're both actually Freescale nowadays, is the company. And the reason I'm going to talk about these is because when you're out there in industry, you may see these things in an old design. And then on the newer side, we'll talk about like PIC from Microchip. We'll talk a little bit about the AVR family from Atmel, but we'll also talk about some of the newest stuff, more interesting, I think, microcontrollers out there now. So the HC12 is a 16-bit microcontroller. It had a complex instruction set. If you don't remember what that means, a complex instruction set is an instruction set with assembly instructions that would do relatively complex operations. So for instance, a string compare operation. Whereas a reduced instruction set computer, or RISC architecture, is one that has instructions that are very very simple, like add or multiply, things like that. It had 6 different addressing modes. Addressing modes are just different ways of getting at data. You can provide an address directly, or you could maybe use a pointer, so that those are 2 different examples of addressing modes. It had many peripheral components, and we'll see that. So a lot of them look similar. It had a commercial C compiler, but a lot of people actually started programming these things in assembly because the C compilers weren't very good back then. Nowadays, C compilers are much better, and we can do quite a good job. It used a software stack, so unlike if you did the RAT architecture in 233, you actually had a hardware stack, right? And you could maybe do 16 nested function calls. Most general purpose processors nowadays prefer to use a software stack because there's not that hard limitation. The only limitation is how much memory you have. And then finally, it had sophisticated instructions that had over 190 assembly instructions. So for reference, like the RAT architecture that was built in 233 had something like 60, right? Okay, so here it is. Here's the top-level block diagram. It had a voltage regulator, some memory. Hey, here's the CPU. It's right here. So this little small block. Yeah, some interrupt capabilities. It has a PLL, a phase lock loop for generating clocks. And then I guess there's some general purpose I/O here. We see DDRA, DDRB, data direction registers, port A, port B. That's actually where you read or write from. In the ATmega, we had pin A and pin B, and then pin A and port A. Here they only have one register for reading or writing. And then we can also notice some other things that we know. Here's an SPI here. Here's a UART, it looks like, RxTX here. So you'll note timers, PWM modules. So a lot of these things are very, very similar to what you would be doing. Okay, so the 68000s are 32-bit processors, and they're a bit higher performance. And nowadays, you can't actually buy one, but you can actually license the core and put it on like a system on chip, or put it on FPGA. And it had a large address space in many addressing modes. So we can run actually a full operating, like a Linux operating system on there. The original Macs, if you remember, like the Mac 2E and stuff, had these processors in there. Back in the day, they also put a lower power version of these things into something called like the Dragon Ball PDA, or the Dragon Ball version of the 68000, which has nothing to do with the anime. There are dozens of C compilers out for this, so that was pretty nice. It only had 8 32-bit data registers and then 8 32-bit address registers. So the address registers were one way you could actually have an addressing mode, a different addressing mode into memory. It had a 32-bit program counter, 32-bit stack pointer, status registers, and I guess one of the interesting things is you started to see supervisory versus user mode. And so anytime you have a system where you're going to allow people to run their own applications on it, then this type of thing becomes important, because that you don't want the user's application from overwriting the operating system or getting at access to memory that it's not supposed to. It could be a security concern as well. Okay, so now we'll talk about like the PIC architecture. This is an 8-bit microarchitecture with 12 to 16-bit instructions. So it's, in some sense, this is very similar to the RAT processor. It's an accumulator-based system where there was one register called W, and if you added something, if you added 2 values, those values would be put into the W register. And then if you want to add 2 other values, you had to move the data out of the W register to someplace else. Accumulator-based systems are not very popular because they require lots of data movement, not very efficient essentially. There's a hardware stack just like the RAT architecture, as we mentioned, and there's an indexed addressing for file select registers, that allows us to address specific blocks of memory, and really is kind of a thing to allow it to expand to larger and larger memory addresses. So the PICs here, they got down to 6 pins. That's pretty crazy, right? 6 pins. You need a power and ground, so you have 4 IOs. Hey, that's cool. But they get up to 100 pins here. We can see here that program memory can be, this is up to 3 kbytes, but can be up to 128 kbytes up here. 5 million instructions per section, up to 16, right? So these are very low performance microcontrollers, but very inexpensive as well. So down here in this range, they cost less than $1. Very few GPIO pins on the PIC. Good for small scale appliances, small size and cost, and low power. Very limited instruction set. You're not getting a lot of performance out of this thing, and very little memory. For the PICs, I've actually never used this, but I have students who've used MPLab, and they really like it. It's free. It's kind of like a Atmel Visual Studio or whatever it's called, right? Okay, so Atmel developed in Norway. We know some of this stuff, right? That the processor is actually pretty fast. It's the first processor that had all their data in flash memory, which is really nice because then you didn't need a separate chip outside of your microcontroller to hold your program memory. Nowadays, most microcontrollers also have flash memory, so it's no longer unique to the AVR architecture. As we saw, there are 32 general purpose 8-bit registers. And those 3 16-bit register pairs, so when you do, let's say, an 8-bit multiply, you can actually generate a 16-bit result, right, when you multiply two 8-bit numbers together. So they have register pairs. And there's support for stack and RAM, so it's a software stack. And we've seen this diagram before. Here's the 32 general registers, each of 8 bits and an ALU, and so we can do computations this way. We can do a computation over here and then write it to RAM. We can read and write from I/O devices, things like that. And then there's a control structure here. So the AT-Tiny is their smallest, 8-pin package, 5 GPIOS. 500 up to 512 words in flash memory, pretty small stuff, right? It's got 8 interrupt sources, 2 8-bit timers, not even a 16-bit timer on there, 4-channel 10-bit ADC analog comparator, can operate between these voltage ranges, has 1 SPI, and in-circuit reprogramming through SPI. And then they have a mid-range guy, right? And this is kind of a little bit closer to our ATmega 328 here. Yeah, I guess that's it for ATmega. Now I want to talk about DSPs. Digital signal processors are microcontrollers that are specifically designed to work on signal processing algorithms. And the killer app in signal processing is filtering. And a filter is at its heart, and like a filter tap or a single order filter is it's a multiply. Right, we're going to scale some sample by some value and add it to another sample that was also scaled. So it's a multiply and an add, multiply and add. And so they actually, in DSPs, digital signal processors, they actually have a piece of hardware there that in a single cycle can do a multiply and an add. The other thing is that when we're doing a filter thing, we need to read a sample and we need to multiply it against a coefficient. And so we need to actually be able to read two things of data at the same time. And so many of them use a modified Harvard architecture where we have one address bus into memory just for instruction, and then 2 data address buses and 2 data buses coming out of memory for reading the sample as well as the coefficient. And so basically we're able to support a single order filter in a single cycle at least. And many of these DSPs have more capabilities than that. But so it's really tuned to do all these digital signal processing things like audio or video, communication sonar, biomedical imaging type stuff, robotics. So Texas Instruments is the largest manufacturer of digital signal processors, and their processors use very long instruction word processors. What that means is that each instruction is actually very long. Instead of fetching one instruction, let's say you have one 32-bit instruction with an opcode and all the registers and all that stuff, you're actually going to fetch maybe 8 instructions all at the same time. And so that it'll literally be 8 times 32, or 256 bits of instruction that you get in a single cycle. And basically then you'll have to make sure all the instructions that are all on the same line of this very long instruction word don't interfere with each other, meaning that one instruction doesn't use the result of another instruction in the same 256-bit very long instruction. And so it's kind of a big compiler problem, and it's not always you're not always able to fill up all 256-bit instruction, 256 bits of a very long instruction word. So you don't quite get 8 times the performance, even though you're fetching 8 times the instructions. But because digital signal processing, we're usually dealing with a lot of data parallelism, we can actually use these architectures quite efficiently. Here's what the C64 looks like. It's got actually two 32 entry register files here, and it can do each of these things all in a single cycle. It can do a logical operation, it can do an arithmetic operation, it can do a simpler data operation, and it can do a multiply operation, and it can do all 8 of these things at the same time. It's not completely flexible. Apparently you have to shift. If you wanted to use some data over here in register file A, you'd have to transfer it over, and you can only do that once per cycle. But that's kind of the general idea here. Okay, so the biggest difference between the microcontroller that you used and the microcontrollers that you may use out there is something called system on chip. And basically a system on chip is saying, okay, we're going to have a microcontroller basically, but we're going to put other things on there, other peripherals. We're going to have maybe code accelerators. So let's say you're Apple and you wanted to you have a lot of money, you can make a system on chip for your iPod that is basically an ARM core with an accelerator that accelerates MP3 encoding decoding, because that's that's what an iPod does a lot of. And if you do that in some accelerator, you can maybe reduce the power consumption of the thing, and it'd be much better for your battery life for your iPod. And then other things like memory controllers, like direct memory access. Okay, so Texas Instruments had the OMAP architecture. I'll actually skip to the, let's see. No, we'll go back to it. So this is the OMAP 44X. They have two ARM Cortex A9s here. These are high speed, can be up to like a gigahertz. Microcontroller cores that they license for ARM Acorn research machines out of England. And then they have a graphics accelerator here and an image signal processor. And a lot of this stuff is borrowed from their C64 architecture type stuff, hardware accelerators. And then some things that look familiar, like timers, interrupts, that type of stuff. Encryption stuff, a lot of these systems have encryption, so you want to maybe encrypt everything that comes on and off the chip because you don't want anybody to be able to reverse engineer your project or your code. And then they have all these other things that may look similar: I2C, serial I/O, UARTs. BSP is it sounds like something from McDonald's. It's just a serial I/O. It's configurable as, let's say, SPI or some other serial interface. USB drivers run on chip. HDMI, another one. Lots of different, here's a JTAG. We talked about JTAG, a flash controller, interface for microphones and keypads and things like that. All these can be on the chip. And what TI is really trying to do is they also sell chips for all these other things around here, like GPS, cameras, speakers, things like that. So they're really trying to sell you an entire solution here. So Freescale makes this applications processor here. It's an interesting, it's got a vector processor on here, so it's kind of like VLIW for, it's got an ARM core on here, another about gigahertz ARM core. It's got cache memory here. Cache memory is basically a copy of recently used instructions and or data, and it's caches are usually small but fast, so, if you have to go access a large memory, which is slow all the time, then you can't get the processor to go very fast. So hopefully most of the time you're executing out of cache, right? And so if you're a CPE student, you study this at length. But basically that's what cache is. It's a recently used memory data in an instruction memory queue. And then again, we see some other things here like PWM, real-time clocks, GPIO, timers that are pretty standard type things. We saw a lot of connectivity things, let's say I2C and UART. But there are other different things like the CAN driver here. A CAN is usually for automotive or maybe aircraft type things. It's a serial protocol with extra reliability built in. Don't want to crash your plane. Then we have memory controllers for different types of memory, like DDR memory, image processing type stuff, and then some system control and boot up. Parallel Parallax makes the Propeller. This is a funny processor. Basically, they have 8 little tiny processors here, and each of them in this little, what is this, a 32-pin package. And so it's a multi-core architecture. Each of these cores get time division multiplexed access to all of the pins. And so every 8th cycle, cog 0 here can access the pins. And every 8th cycle, the cog 1 can go get access to all the pins. And so it's kind of I call it a draconian way of managing I/O. It's probably not very efficient, but it does avoid some problems with resource sharing in a multi-core architecture. So I thought it was fun to look at. And so you can take a look at this in more detail if you're interested. Cypress PSOC5, I have some experience with this. This is an interesting system. In here you can either have an 8051 or an ARM Cortex M3 CPU. It runs like 60, maybe 70 megahertz-ish. And then memory and stuff like that. We have some built-in I/Os, like general purpose I/Os, for instance, serial I/O, USB. But it also, we have reprogrammable digital fabric here, and it's more of a CPLD rather than FPGA. Remember, a CPLD uses like and/or planes with muxes. Where an FPGA uses lookup tables, so it's more of a CPLD. And using this type of stuff, you can actually build things. So here they show you, okay, these 3 UDBs can be actually an I2C slave. If you use 2 UDBs, you can make a UART and things like that. So it's kind of interesting. The other interesting thing here is really the analog reprogrammable fabric. You have a whole bunch of op amps and switch capacitors that allow you to create different gains using these op amps. So you can have them in, I don't know, inverting amplifier or non-inverting amplifier or whatever it is. You have ADCs of different types, some DACs, and then some other like a digital filter block and stuff. So you can actually do some like filtering here in the analog subsystem rather than doing it here in the digital subsystem or on the CPU itself. Okay, so the last one I'm going to talk about is the Zyng architecture. The Zyng architecture is by Xilinx. This is really an FPGA, if you ask me. Here, many system on chips use this AMBA bus, I guess. It's a standard bus where other people can generate their own IP or intellectual property and actually have them connect to the AMBA here, AMBA standard bus, and then that'll allow you to connect to the ARM processor in here. So there's an ARM processor with an floating point units and an ARM Cortex and cache and memory and timers and on-chip memory and stuff like that. And then it has some other built-in general purpose I/O stuff like that. And then it's got FPGA fabric around here. All this yellow stuff, I guess, is general purpose I/O. And then they have high-speed gigabit transceivers here for doing high-speed communication. So it's a pretty amazing integration of stuff. I don't know if you ever thought you could go into business for yourself. One place where you could actually do that pretty easily is you could actually create your own IP, right? You could create your own block, let's say an MP3 decoder block or something. There's probably enough of those around that you probably want to find something else. But you could actually interface them into this AMBA bus, and you could own a whole bunch of essentially VHDL or Verilog with some support documents, and then you could also do some consulting on the side and go into business for yourself. And a lot of people do that. Okay, that's it. Thanks.